This video is going to be a little bit of review, and then we're going to add on to what we already know by exploring more about spectroscopy over a wider range of electromagnetic radiation. So remember, electromagnetic radiation is all the same stuff. It's a in-phase pair of magnetic field variation and electrical field variation that travels through space. And when the wavelengths are long, they are lower energy. That's redder if it's visible light. When the wavelengths are shorter, it's bluer or more violet if it's visible light. But then there's also light that's too blue for us to see, ultraviolet, X radiation, gamma radiation, and too red for us to see, infrared, microwave, radio waves of all kinds. We will also remember that Max Planck discovered that there was a wave-particle duality to light, and that light always doesn't behave like a wave every time, and sometimes it's more behaving like a particle. And then the photoelectric effect was a consequence of this. Remember that when the wavelength is short enough, or when the frequency is high enough, or when the energy is high enough, then electrons can be ejected from the atoms, and when that happens, that's called the photoelectric effect. A consequence of that was that they came up with this understanding of a photon, which is a particle of energy of electromagnetic radiation, and the amount of energy that each photon carried could be quantified by taking Planck's constant, which was 6.626 times 10 to the negative 34th joule seconds, and multiplying that by the frequency in hertz. And that would tell you how much energy each photon carried. And remember that light from excited atomic samples has a discontinuous spectrum. So unlike the full complete spectrum that you would get from ordinary white light, a hot sample of a pure element would give you a spectrum that only had certain colors in it and all the colors were missing. And if you passed light energy through a cold sample of that same gas, you would get exactly the negative. You'd have the complete spectrum, but only with those lines emitted. And so they had to come up with a model that explained that, and this was this energy level model that they came up with. Big transitions from one level to the next would provide more violet light of higher energy, shorter wavelength, and then smaller transitions between energy levels would provide light that was less violet, longer wavelength, smaller energy for the photons that were coming off of there. Removing an electron completely from the atom is essentially moving it to energy level infinity. And according to this equation that Bohr developed, which still works pretty good for understanding this, that would make n high, in this example, infinity. And that would mean that that would be the way that you could quantify how much energy it would take to ionize the atom, or in other words, cause the photoelectric effect, because 1 over infinity is essentially 0. The name for that amount of energy is called the binding energy. And if we look at comparisons of the energy of the photon and the binding energy of a particular electron in an atom, nothing will happen if the binding energy is bigger than the energy of the photon. But if the energy of the photon is greater than the binding energy, then not only will the electron be ejected from the atom, but it will also carry some extra kinetic energy. And then they used that to develop the PES spectrum that we learned about earlier. So just a review of the photoelectric effect. If the energy of the photon is less than the ionization energy or the binding energy, nothing will happen. If it's exactly equal, it'll eject an electron that has no extra kinetic energy. But if it's greater than the ionization energy, then not only will the electron be ejected, but it will be moving with some kinetic energy. It turns out that for the photoelectric effect to occur, so we're talking about this region here, you have to have energy that's coming from the visible area of the spectrum and the UV area of the spectrum. That's sufficiently high energy to cause the photoelectric effect. If you have infrared radiation or radio waves or microwaves, things that are on the longer end of the spectrum, they will not be energetic enough to cause the photoelectric effect. So these electron transitions between energy levels are coming from the visible and the UV part of the spectrum. Even though infrared radiation cannot affect energy level transitions within the atom, it doesn't have no effect on matter. So these lower energy wavelengths can't cause electronic transitions. What they do is they can cause vibrations and rotations in molecules. So in the near infrared, and by near infrared we mean kind of close to red, close to what we can see, but still infrared, still too long for us to see. This causes vibrations in molecules, like this. And different wavelengths will cause different vibrations. This tool from the University of Minnesota can give us a kind of a visual feel for what we're talking about here. This is a molecule of propene. The gray atoms are carbon and the kind of white atoms are hydrogen. You can see there's a double bond and there's a single bond between the carbons, and then there's single bonds to some hydrogens. If we look at the infrared spectrum for this atom, this shows the absorption of infrared radiation that would be taken in by this molecule. And when we click on these different peaks here, like this is wave number 500, if I click on this, it shows what mode of vibration that amount of energy could cause. Here's another mode of vibration if I click on this one. Slightly different way of it wiggling around. So there's like torsional bending. Here's another one. Here's another one. And we can see that the more energetic ones are now causing bending in other places. And if I go, there's a kind of another little grouping here with the higher wave numbers. If I click on those, we can see that not only is it bending, but now we're seeing some modes of stretching occurring between the bond lengths. So that's what happens when infrared radiation is directed at a molecule. So as we saw, different wavelengths can cause different modes of vibration. There's some twisting, there's some stretching, and each particular wavelength of infrared radiation is going to cause a slightly different mode of vibration. The infrared spectrum that we looked at for absorption is a little bit upside down and cleaned up from what a real IR absorption spectra looks like. So there's a sort of a baseline that's at the top there. That would represent no absorption. And then there are some spikes that go down into the graph, and those represent the wavelengths that are absorbed to cause these vibrations. And the deeper the spike, the more of that energy is absorbed, which would mean the more of that type of vibration there is. So let's say that this, for example, represented a certain kind of stretching of a double bond. Well, if you saw a lot of that energy being removed, then that would mean the molecule you're looking at has that kind of a double bond that can do that kind of a stretching. And so these IR spectra, for people who really know what they're doing, and it's a very specialized science, can be almost a fingerprint for molecules. So you could start to put together what is the structure of the molecule. And organic chemists who are very adept at this can read these spectra right away and come up with a very good idea of what the structure is going to be like, especially if they have other information to use, like what's the molecular formula. It should also be noted that these are not wavelengths. These are the reciprocal of wavelength, which is the wave number. So the bigger this number is, the shorter the wavelength is. The other zone is microwaves. So this is the far infrared. And it's a little bit farther away from what's visible for us. These are not energetic enough to cause vibrations like twists and stretches. All they can do is cause the molecule to spin. So when a molecule is bombarded with microwave radiation, that's just going to cause it to spin in different modes. And in fact, that's how microwave ovens work. The water molecule or other polar molecules like water will spin when they're bombarded with these microwaves, and that's the whole purpose. That spinning is kinetic energy, and it causes even more kinetic energy when they collide with neighboring molecules.